Hello, welcome to our lesson today on influence line. My name is Engineer Dr. Elidum E. Ambrose from the Department of Civil Engineering at Akwa State University. So we are going to look at a lesson today on influence line, which is a method of analyzing structures in structural engineering. Kindly subscribe to this channel if you have not, so that you'll be getting videos as we publish it. And so, why do we need influence line? So far in structural analysis, what we have been doing have been cases where the loading system on the structures are fixed in position on the structure. And so we analyze usually the support reactions, the shear force, the bending moment diagram, and the deflection of those structures. However, there are some types of structures in engineering where the loading could be located at one or a number of possible positions, and indeed may be moving across a structure. Example of such can be seen in a train crossing a rail bridge or a number of cars crossing a road bridge simultaneously. So influence line is a graphical method of presentation that is used to analyze the effect of moving loads on systems, on structures. For instance, consider the case of a system of moving loads across a road bridge. The maximum effect, that could be the support reaction, shear force, bending moment, etc., etc. Then their maximum effect will not only depend on the number and magnitude of loads, but will also depend on their relative positions and locations on the span. So in analyzing such moving loads, we need the method of influence line. Let's start by analyzing support reactions. Let's say we have a beam here with a road bridge or rail bridge, which has a span of L, and he has support here at A. Support A we call VA. He has support at point B, we call it VB. That's reaction at B. Reaction at B is VB. VA is reaction at support A. Let's place a 1 kilonewton load anywhere within this band. So taking our origin A, support A as the origin. So the load is at a variable location. That's why we put X here. X could be anything. X could be 0. X could be L. And so let's start analyzing. From equilibrium principles, when X is 0, that means this 1 kilonewton load is directly on top of VA. So when X is 0, if you use equilibrium, the concept of equilibrium, VA will be equals to 1 because all this load is directly on top of VA. So VA will be 1, that is reaction at A will be 1. And when X equals to L, when X is this distance equal to L, that means VA will be directly on top. The 1 kilonewton load will be directly on top of the V of VB. In that case, our VA will be 0, reaction at A will be 0. You can use the concept of equilibrium of forces to analyze that. Now, similarly, when X equals to 0, that means when the 1 kilonewton load is directly on top of VA, VB will be equals to 0. VB will be equals to 0. And when X equals to L, that is when this 1 kilonewton load is directly on top of VB. In that case, VB will be equals to 1 kilonewton. So with the above information, we can plot the influence line for reaction at A, that is VA, and reaction at B. Let's start with this one, reaction at A. So remember when X is equal to 0, VA was 1. That means at this point, VA, the magnitude of VA was 1 kilonewton. That's why we have 1 kilonewton here. When X was equal to L, that means at this point, VA was 0. VA was 0. So we now plot the graph of those points. 1 here, 0 here. We just join it together and we have a graph. And this graph is an influence line for A, for VA. That is influence line for reaction at A. You can use the concept of similar triangle to find the coordinate, the length of this at any point. For instance, here at this point 0.2L, this from the left hand side, if you use the concept of similar triangle, you notice that this height is 0.8 kilonewton. If this place is 1, the same thing here, this is 0.4 kilonewton. So we also can plot the influence line for reaction at B by using the information we have here. When x equals to 1, VB was 0. When x equals to L, VB was 1. So we plot it. When we plot it, it gives us this triangle, and we say that is the influence line for VB. That is influence line for reaction at B. Again, we can calculate the coordinate at any point using the concepts of similar triangle. If this place is 1, this place will be 0.6, this place will be 2, considering the distance here. So with that, we have been able to plot the influence line for reaction at A and reaction at B. So from the influence line, we say the value of VA and VB can be computed respectively when any load is applied at any distance within the spans. Now, the value of VA and VB can be calculated for any magnitude of load or combinations of load. For instance, now, if loads of 18 kilonewton and 25 kilonewton are applied at 0.2L and 0.6L respectively, we can calculate the reaction at support A and support B. That is, if we have, say, 0.18 kilonewton load is applied at 0.2L. So where is 0.2L? This is 0.2L. That means the 18 kilonewton load will be applied at this point. Now, the 25 kilonewton load will be applied at what? 0.6L. And 0.6L is actually here. This is 0.6. So what we do, that is this point at this point. So all we need is to come and calculate the coordinate at this point using the concept of a similar triangle. So if this place is 1 kilonewton, this place is 0.8 kilonewton. So if we place the load here, the load of what? 18 kilonewton. The reaction at A, the effect of that load will be the magnitude of that load multiplied by this coordinate. This one will also plus, this one will also be the magnitude of this load multiplied by the coordinate. So that's why we say reaction at A is equal to 0.8, which is this magnitude, multiplied by 18, which is the 18 kilonewton load that is here, plus 0.4, which is the magnitude at this point, plus the 25 kilonewton load, which is on top here. So by the time we do that together, we have 24.4. That is the reaction at A due to two loads being at those positions. And for reaction at B, this is the influence line for VB. So what are the coordinates at the point? Remember, we said that the 18 kilonewton load is here, and the coordinate using similar triangle is 0.2 for VB, and the 25 kilonewton load is here, and the coordinate here is 0.6. So when you come here, you can do 0.2 multiplied by the magnitude of load plus 0.6 multiplied by the magnitude of load there. It gives us 18.6 kilonewton. So you can see that if you have two loads that are positioned at 0.2L and 0.6L, this will be the reaction at A, 25.4 kilonewton. This will be the reaction at support B, 18.6 kilonewton. And so let's look at shear force. Let's also look at shear force. How do we draw influence lines for shear force? So let's look at this, our beam, our usual beam of span L. and we place a 1 kilonewton load at a variable position along the beam. That's why we make this place X. And so let's start getting information so that we can draw the influence line, plot the influence line for reaction for shear force. So let's consider shear force at midspan. Shear force is always calculated at a particular point. So we want to draw the influence line for shear force at midspan C. Now, when x equals to 0, that is when this 1 kilonewton load is directly on top, we know that VA will be 1. The reaction at A will be 1 kilonewton. So if we have 1 kilonewton here, we need to find the shear force. And remember the definition of shear force. That shear force is the algebraic sum of all the forces either to the left or to the right of a section in a beam or in a structure. So if we want to find shear force, if the 1 kilonewton load is here, there will be two load on the left of C. We are using the left hand side now, which will be the VA and the 1 kilonewton load. And the 1 kilonewton load will be directly on top of VA, such that shear force there will be the VA, which is going up positive, and the value of VA is 1, minus the 1 kilonewton load, which is coming down negative. So we have VA minus 1, and VA is 1. So shear force there will be 0. The next point we need to find the shear force value will be at point C. But at point C, if you remember shear force very well, you're going to have two values of shear force, one just before C, one just after C. So let's say when x equal to L over 2, that means when this 1 kilonewton load is at point C. Okay, the first one is when it's just before point C. When it is just before point C, that means you will consider the 1 kilonewton load. So when that happens, what will be our reaction of VA? VA will be 0.5. So the load 1 kilonewton is at midspan, halfway between VA and VB. So VA will be 0.5. You can go into use equilibrium principle to analyze that. So if VA is 1.5, our shear force now will be VA is going up and the 1 kilonewton is coming down. So it will be VA minus 1 and VA is 0.5. So you have minus 0.5 kilonewton. And so you now do again at that same point when x is just after C. So if x is just after C, there will be only one load by the left hand side of C, which is VA. And we say that VA is 0.5. So that means shear force at C will be what? It's equal to VA and will equal to 0.5 kilonewton. So the next thing is when x equal to L. When x equal to L, that means the 1 kilonewton load is here, directly on top of VB. At that point, VA will be 0. And shear force there will be equal to only VA, because VA will be only the only force at the left of C. So VA, shear force will be VA and will be equal to 0. So we can now use this information and plot the influence line for shear force at C. So you see the influence line. This is when x equals to 0, shear force is 0. When x is equal to C is equal to half L over 2, just before C, you have minus 0.5. When it is just after C, you have 0.5. So this is negative, this is positive. And when x equal to L, you have the shear force is 0. So that's how we plot it. So this is the influence line for shear force at midspan of that beam. We can go ahead, let's solve example. You need to take note of this, that the influence line diagram for shear force at midspan is different from shear force diagram. The influence line diagram shows the shear force at a fixed position on a beam for a unit load at variable position across the beam. That means you want to see how does the shear force varies at a particular point as the load moves from one point to another. Whereas for shear force diagram shows the variation of shear force across a span for a fixed position load. So for shear force diagram, the load is fixed and you are plotting the variation of the shear force across the span of the beam where the load is applied. So go back to example 1. Example 1 say calculate the shear force at midspan of the beam shown in figure 2 if concentrated load of 25 kN and 30 kN are applied simultaneously at 0.2 L and 0.4 L from support A respectively. So this is the load. We have 25 kN applied here at a distance of 0.2 L. We have a 30 kN load applied here at a distance of 0.4 L. This is a shear force diagram that we have plotted. So what we need to do, just under the load on the shear force diagram, we compute the coordinate. I mark the length here. So if this place is 0.5, using similar triangle, considering this distance, this place will be 0.2 kilonewton, this will be 0.4 kilonewton. So once we know that, to get the shear force at C, it will just be this 25 kilonewton load multiplied by this coordinate plus this 30 kilonewton load multiplied by this coordinate. But remember that this coordinate and coordinates are negative. This 0.4 is negative, this 0.2 is negative because this is the negative section of the shear force diagram of, of the influence line diagram for shear force. So we now go and say shear force equals to 25 times minus 0.2 plus 30 times minus 0.4. It gives us minus 17. The essence of the minus is just to show that the shear force is acting downward. If it was positive, we would have shown that the shear force is acting upward. All these things are based on our sign convention. So let's look at influence line for bending moment. And remember, all this one we are looking at for concentrated load. So let's use the same loaded beam to develop influence line for bending moment at midspan. So this is the beam, our usual 1 kilonewton load at a variable length distance across the beam, reaction at A, reaction at B. And so when x equals to 0, when this 1 kilonewton load is directly on top of A, what will be reaction? Reaction at A will be 1 kilonewton. And what will be the bending moment? We have to define bending moment again. That bending moment is the algebraic sum of the moment of forces either to the left or to the right of a section. So if we stand at point C, we are taking bending moment at point C. We say when x equals to 0, VA equals to 1 kilonewton. That means when x is 0, the 1 kilonewton load will be directly on top of VA. So there will be two loads by the left and right side of C. So we are going to take the algebraic sum of the moments of those two loads. And so VA, because VA is going up, is positive. What is the perpendicular distance? Moment is force times the perpendicular distance. The force is VA. The perpendicular distance from here to where we are taking moment is L over 2. That's why we have VA multiplied by L over 2. Now the 1 kilonewton load will still be directly on top of A, and the perpendicular distance will also be L over 2. It will be minus because it is coming down. So you have minus 1 into L over 2. And if you do this, because VA is also 1, so the whole of this will give you 0. So shear force at point A, bending moment at point A is 0. Now when x equals to L, when x is with 1 kilonewton load is at point C, our VA will be 0.5. VA will be 0.5. And then what will be the bending moment? The bending moment when this load is there will be only one force by the left hand of C to take moment. The 1 kilonewton will be exactly there. The perpendicular distance will be 0. So the moment of that 1 kilonewton load will be 0. So it will be VA. The bending moment there will be 0.5, which is our VA, multiplied by the perpendicular distance L over 2. that will give us 0.25 L. And so the next is to take when x equal to L. When x equal to L, the 1 kilonewton load will be directly on top of VB. Will be directly on top of VB. And so VA in that case will be 0. So when x equal to L, so when x equals to L, VA will be 0. And bending moment there will be VA multiplied by the perpendicular distance. Since VA is 0, bending moment will be 0. And so we can go ahead and plot that information that at this point, when x equals to 0, bending moment is 0. When x equal to L over 2, bending moment is 0.25 L. And when x equals to L, bending moment is 0. So we can plot and you have this. Remember that for bending moment, positive is down and the negative is up. So that's why we plot this inverted triangle. So example 2 is that use the influence line diagram in figure 3 to calculate the bending moment at midpoint when a load of 15 kilonewton and another of 10 kilonewton are located at 0.2 L and 0.4 L respectively from support A. So this is a loading system. We are told that a concentrated load of 15 kilonewton is located at a distance of what? 0.2 L, and this other load of 10 kilonewton is located at 0.4 L. So from here to here 0.2, from here to here 0.2. That means from here to here 0.4 L. So once you have this, all you need to do is place it on top of the bending moment diagram. Go and find the coordinates of the bending moment diagram at that point. So if we, from our calculation, this place was 0.25 L. Using the concepts of similar triangle, this place is 0.1 L and this is 0.2 L. And so we can now find bending moment will now be the force multiplied by the coordinate plus this other force multiplied by the coordinate. So you have 15 times 0.1 L plus 10 times 0.2 L, and everything gives you what? 3.5 L. Remember, L is the length of the beam. So all those we have been looking have been cases for concentrated load. So let's look at what happens when the load is a uniformly distributed load. So when the load is a uniformly distributed load, all we need to do is the position of the load. We are going to multiply the maximum magnitude of the load by the area of the shade or influence line beneath that distributed load. And so this is what will happen. Let us calculate the shear force and bending moment of the beam loaded with a distributed load as shown in figure 4. This is figure 4. The distributed load is of magnitude W per meter and length 0.2 L. So we have a load of W per meter. W is the magnitude of the load, and the load has a length of 0.2 L. That means from here to here is what? 0.2 L. So we now bring the shear force influence line for shear force that we have plotted. We place it beneath it. We bring the influence line for the bending moment that we have plotted and place it directly beneath the load. So we want to find shear force at C. This is influence line for shear force at C. So to find the shear force at C, we position the load exactly where it was, and we come and find the influence line, the area or beneath the load on the influence line. So this is this shaded portion. Remember that the influence area is what? This is a trapezium. An area of a trapezium is what? Half the sum of the two parallel sides times height. So what is the area of this? That is why we say shear force W is the magnitude of the load, and the area of this is half is the two parallel sides. We also is 0.2 and 0.4. So 0.2 times 0.4 divided by 2, that is half of that, and then times the length from here to here is what? 0.2L. So we multiply by 0.2L. The minus is to show that the shear force is at the negative side. W is the magnitude of the load. So when we do all this, we have minus 3WL. For bending moment, we have also plot the area. We find this coordinate, we find this coordinate. The area is what? The two parallel sides 0.2L and 0.2L. So and 0.1L. This is 0.1L, not 0.2. This is 0.2L. Remember that. So we have 0.2L plus 0.1L over 2 multiplied by the length, which is from here to here, is 0.2L multiplied by the magnitude of the load, and that gives us minus 3WL squared. Give us minus 3WL squared. And so it should be noted that the magnitude of the shearing force and bending moment in this case at midspan, it depends on the magnitude, the length, and the position of the distributed load on the span. So if the load were longer than the span and it entered the span from support A and move across from left to right, now the maximum negative shear force at midspan will occur when that part of the span is left, that is left of C, is fully loaded. That is when the whole of this place is fully loaded. So that is when you have the maximum shear force. Now when the maximum negative shear force, now when the load move completely to the right of C and fully covers the part, the maximum positive shear force then will occur. Now the maximum bending moment will occur when the whole span is loaded. We are talking about a load that is longer than the span of the beam. The same general observations also will be true for other positions other than midspan. So if we are to find out the bending moment influence line for shear force or bending moment at any other point other than midspan, we just follow the same process to derive the influence line diagram for those. So this is where we will stop for this part 1. To continue, please watch the part 2 of the video. Thank you very much.